Okay gang, welcome back. So if you look at this video and you're like, damn, Joe, why is this video so long? All we're gonna do is take each one of our benzene mechanisms that you will be responsible for knowing, I'm sure at pretty much any school, and we're just gonna go through them step by step. I'm gonna highlight some key details and key aspects of each mechanism that you should definitely keep tucked in the back of your head, and then we'll call it a day. So we're just gonna take them one by one. But first, let me kind of break down a big phrase that applies to all of these mechanisms. All of these mechanisms we're going to do today are called electrophilic aromatic substitution mechanisms. Let me make sure I spell this right. Okay. They're called electrophilic aromatic substitution mechanisms. And that seems like a really big, scary word. And we always abbreviate it EAS. But let's just break it down because you kind of know, actually you do know, what this whole phrase means. Alright, electrophilic. That means something that is a lover of negative charge, right? So usually something that's positive. And that's exactly what we're going to do. We're going to take things that are positive, that like, such as Br+, Cl+, and some other things, and we're going to substitute them on aromatic structures. So basically, electrophilic aromatic substitution means the addition of positive things to a benzene ring. Okay? So, the first mechanism we're going to talk about, I think there's 5 or 6, but trust me, you'll see that they're actually all extremely similar and you'll handle them without a problem. Okay, so the first mechanism is called chlorination, and the net reaction looks a little something like this. I'll draw it over here. Take a benzene ring. If you introduce some Cl2 and this catalyst AlCl3, you will get a benzene ring with a chlorine off of it. Okay? So, how does this work? Well, let's figure out. So, kind of the first step in the mechanism is you have Cl2. So we'll draw that Lewis structure. I'll draw in those lone pairs. Okie dokie. Then we're going to introduce this catalyst AlCl3. And you can see he has 3 bonds, so what's going to happen is that he can kind of accept an electron pair. So we'll take this chlorine and he's going to attack the aluminum, the AlCl3. Okay? The result of that electron flow looks a little something like this. Okay? And since aluminum is in that 3rd column on the periodic table, he kind of only wants 3 bonds, but he kind of has like a negative formal charge here, right? And since chlorine just donated an electron pair to make a bond, he has a positive formal charge. Okay, what's going to happen here now is that this bond is going to split, and all the electrons in this bond are going to go to this chlorine. And if we draw an arrow over here, what we get kind of in a net, in that net electron flow, is we get AlCl4. Aluminum has that negative charge. And we also have a Cl+, right? Because this chlorine now only has 6 electrons. Again, you can kind of see in this electron flow, now we have, I'm going to asterisk this over here, now we have that positive piece, this electrophilic atom that we're going to add to our benzene ring. Okay, so now let's kind of go introduce benzene to the mechanism. Now I'm going to take this Cl+, and what I'm going to do is, since he's very positive, remember, this double bond, you know, it's a hub of negative charge, he's going to go ahead and grab this chlorine. If we draw the result of that electron flow, right, I didn't touch these 2 double bonds at all, and you can either pick, you know, to bond the chlorine here, bond the chlorine there, doesn't matter. I'm just going to go pick the top carbon. And that leaves this carbon right here with a positive charge. Okay, so now you can see that we've kind of messed up the aromaticity of the ring, right? And remember in the last video, we said that was a no-go. We said that was very bad. That's why that HCl Markov-Nikov addition did not work with benzene. However, we're going to restore the aromaticity of the ring, and here's how we're going to do it. We're going to reintroduce that AlCl3, or AlCl4, I'm sorry. Remember, aluminum has that negative charge. And what we're going to do is we're actually going to kind of do like a little bit of an elimination reaction, right? We're going to take one of the chlorines. He's actually going to take his his electrons in this bond. He's going to snatch up the hydrogen, the electrons right here are going to swing down and reform the double bond, restoring aromaticity. And what we get essentially, I'm going to draw the products down here, is we get our benzene ring with the aromatic pi electron system restored with a chlorine right here. We then get our catalyst back, AlCl3, and that's good, right? Because catalysts are not consumed in a reaction, right? They're present in the beginning and they're present at the end. And if you can see, right, this chlorine left right here, we made some HCl. That's more of an afterthought. But do you see how this works? Basically, and you'll see this all the time, there's a little unique way in every reaction to produce your electrophile, that positive thing at the beginning, but then this is exactly the same in every mechanism. You add the electrophile to the benzene ring, you disrupt the aromaticity by making this positive charge, then what you're going to have some catalyst that's going to pick off this hydrogen and then restore the ring's aromaticity and produce your product. Okay, what's awesome is that I have these mechanisms all nicely laid out for you guys in a file in the benzene and aromatic section, but we're going to go through the rest of them. So let me erase this, and now I'll show you bromination, which in actuality is just like chlorination. Okay, so now that we've seen how chlorination works, let's look at the electrophilic aromatic substitution reaction of bromination. Let me throw the reaction up here. So again, what you're going to do essentially is we're just going to have our stock benzene ring, and our reagents are Br2, and instead of AlCl3, our catalyst is going to be FeBr3, iron with 3 bromines. So to be completely honest, gang, this is the exact same mechanism, except all we're working with is bromines, and our catalyst instead of AlCl3 is FeBr3. But let's draw the mechanism. Okay, so I'm going to draw our diatomic bromine right here, and I'm going to draw our expanded version of our catalyst. Okay, so just like aluminum, iron is going to have 3 bonds here. So you can see he can kind of accommodate an additional electron pair if someone were to supply one. Bromine's going to do just that. Let's have our bromine swoop in and attack iron, and the result of that electron flow looks a little like this. Alright, we have the bromine having a plus charge because it donated an electron pair, and since iron accepted one, he's going to sport a negative charge. Just like in the last mechanism, this bond is going to break and all the electrons go to that bromine with the positive charge. So if I'm going to draw the result over here, right, we're going to have FeBr4 with a negative charge on iron, and then we make our Br+, that electrophile we're going to plan on adding to the benzene ring because bromine only has 6 electrons. So now let's introduce benzene. Okay? So let's introduce benzene to the Br+. Remember, this aromatic system is a hub of negative charge, right? So let's just use this double bond right here to come out and grab the Br+. From there, right, we disrupt the ring's aromaticity. We don't touch either of these double bonds, but if I stick the bromine right here, we have a positive charge on that carbon. Okay, so what's our next move? Well, let's introduce that catalyst that we were kind of messing around with up top. I'm going to draw all the bromines out, right? And we know that since iron's has 4 bonds, he has a negative charge. So remember, we need to restore this ring's aromaticity to make this reaction good, to make the energetic difference favorable. So let's take a hydrogen from where that bromine is we just added, and this bromine right here is going to take his bond to iron. He's going to grab this H to become HBr, and kind of in an elimination fashion, like we saw in the last mechanism, these electrons will swing down, form a double bond, and restore the ring's aromaticity. So if I draw the arrow over here, but I draw the products down here, right? Again, we have now our halogenated benzene product right there, and we've restored the ring's aromaticity. That's a good energetic thing. Then we have, we've recovered our catalyst, right? We now have FeBr3 again, because that one bromine left, and remember when that bromine left, he formed HBr. So you can see that there is no difference at all between this mechanism and the one involving Cl2 and AlCl3. we just swapped out our chlorines for bromines and our aluminum for iron. Again, I have this mechanism on the sheet that is on the benzene and aromatic section, but let me erase all of this. We're going to get a little bit different and a little more interesting on the next mechanism, which is called nitration. Alrighty gang, so now that we're finally done with chlorination and bromination, we're going to move away from adding halogens to a benzene ring, and now we're going to do a reaction called nitration. Same type of deal, it's still another EAS reaction, just a little different. So if you can see, if we have a benzene ring and we add HNO3, some nitric acid, along with some catalytic H2SO4, then we get a benzene product with what's called a nitro group, which is that NO2, a nitro group. Okay, so like we've seen before, the process is produce your electrophile, then add it to the benzene ring, disrupt that aromaticity, take a hydrogen where you added that group, have something pick it off, take those electrons, swing them down into the ring, restore aromaticity, and then we're done. So let's do it. Okay, so one thing you're going to need to know is the Lewis structure for HNO3 and the Lewis structure for H2SO4. So if we draw the Lewis structure for nitric acid, looks a little like that, okay? And if we have the structure for H2SO4, looks a little like this, okay? So what's going to happen here is that H2SO4 is actually going to protonate this OH group on the nitric acid. So let's kind of grab that H and we'll dump those electrons onto this oxygen right there. Let's draw the result of that electron flow. Okay, you can see all we've done is protonate this oxygen here. And if you look, that's a good leading group. That's water, right? That'll come into play in just a second. And then we have this leftover ion from sulfuric acid, okay? And we'll bring him back in a little bit. Okay, so we're going to kind of ignore him, but let's look at what's going on here, right? I'm going to redraw him down here. That looks like a good leaving group, right? That H2O right there, that's with the oxygen with the positive charge. So here's what's going to happen. He's going to straight up just peace out. He's leaving. And at the same time, when that happens, right, nitrogen's losing a bond. So what's going to happen is once this bond breaks and water leaves, an electron pair from this oxygen with a minus charge is going to swing an electron pair down. So, you know, I'm going to kind of put minus H2O because water's leaving, and we produce this NO2 right here, nitrogen still having the positive charge, and this right here is our electrophile, right? This is the thing we're going to add to benzene, which is good. So now, let's go ahead, let's draw benzene, and we'll introduce this NO2 right here. Remember, benzene, full of negative charge, he's very interested in this nitrogen because he has a positive formal charge, right? He is literally positive. So let's just use this bond right here. We're going to come out and grab that nitrogen. Some bond has to break, otherwise we're going to violate the octet rule. So let's just kick an electron pair up here. So at this point, once you add the group to the benzene ring, right, we didn't touch these two double bonds, you can just abbreviate the group, the nitro group, as NO2. So no need to kind of draw this expanded anymore. And remember, we have a formal charge on this carbon because when we use this bond to grab the nitrogen, he's kind of left out. He's a little SOL. Okay, so now we need to restore the ring's aromaticity, right? Otherwise, this is going to be energetically unfavorable. Well, let's take our catalytic piece, right? It's not a AlCl3 or an FeBr3, but it's an acid this time. So let's draw him out. So what's going to happen is this negative oxygen right here, he's going to be the one that's going to grab this hydrogen to then allow these electrons to swing down, form a double bond, and regain the ring's aromaticity. So let's do it. And we've done this plenty of times already, right? We see that this is a recurring theme. So if I'm going to draw an arrow over here and write the products down here, you can see we have a benzene ring with a nitro group on it now, an NO2, and we've reproduced this H2SO4 that we started with. And that's good, right? Because we said it was acid catalyzed. So we started with the H2SO4 and we ended with the H2SO4. So just remember, from this point where you add stuff onto the benzene ring, pick the H off, swing the electrons down, that's always going to be the same, I promise you. The only difference comes in the beginning in producing your electrophile, that positive atom or molecule. Here we just had to protonate this OH group to water. He left, we swung electrons down, and then we had our nitro group ready to go. Okay, let me erase this, and then the next mechanism we're going to talk about is called sulfonylation. Okay, so I may have misspoke in the last episode. Instead of sulfonylation, we're just going to call this sulfonation. But here's kind of where we're headed. So if you take, you guessed it, a plain benzene ring, and then you add a little SO3, some sulfur trioxide, along with, again, some more catalytic H2SO4, some catalytic acid, then you're going to then put on a benzene ring what you would call a sulfonyl group. Okay, so let's see how we do it. So, one thing you're going to need to remember is the Lewis structure for SO3, but it's pretty basic. It's just sulfur double bonded to 3 oxygens. We're going to then introduce our sulfuric acid. So make sure to remember that Lewis structure because it's going to come up a few times. And what you're going to do is you're going to protonate one of these oxygens. But the best way to do it is to just take the electrons from a double bond from one of the oxygens. So let's have the oxygen grab this hydrogen, and the protonated product looks like this. And this leaves sulfur with a positive charge, and then we have our conjugate base of the H2SO4 with the oxygen bearing that negative charge, and we will see him in a little bit. We're going to bring him back, as you saw in the last mechanism. What's great is that we have our electrophile ready to go. Right, you can see we're going to bond this sulfur directly to the ring, and he's bearing a positive charge, so we're ready to go. We're ready to do the exact steps that we've done roughly 3 or 4 times right by now. All right, so let's introduce this positive piece right here. Again, I'm going to say it again just to be repetitive and to really hammer it home. But remember, this benzene ring is full of negative charge. I'm going to take the negative electrons in this double bond, and I'm going to grab the sulfur. And you can see since sulfur's making 6 bonds up here, because he can expand his kind of octet, then we don't need to bounce any bonds at all. So what's nice is just like in that nitro mechanism, I don't have to draw the expanded version of the sulfur thing anymore. I can just write SO3H, because right, we have S, 3 O's, and an H, just like we do up there. But remember, we didn't touch these double bonds at all. Since this carbon got to bond to the sulfur, this carbon is now a carbocation. Remember, we need to restore the ring's aromaticity. And just like we did in the last mechanism, let's kind of grab, the conjugate base of our catalytic acid to kind of help us out. Right? That oxygen has a negative charge. He is no problem picking off this proton to then allow the electrons from that bond to swing down and restore the ring's aromaticity. So I'm drawing my arrow over here, a list of products down here. What we have going on is the restored aromatic ring. We now have a sulfonyl group attached, and as well we have recovered our catalytic acid. Okay, so you can see that this is almost the same thing over and over and over again. But just make sure that you go back and practice these and nail these down. We have 2 more left. One's a little interesting because there's the possibility of carbocation shifts, throwback to OChem 1, and then another mechanism which is kind of a variation of that one. So in the next part of this video, we're going to talk about Friedel-Crafts alkylation. Okay, gang, so now we're going to do an EAS reaction, and this is kind of cool. We're going to start being able to add into our repertoire the ability to add organic pieces onto a benzene ring. So this mechanism, this reaction, is called Friedel-Crafts alkylation. And you've seen this word before. To alkylate means obviously to stick on an alkane piece, to stick on some organic piece. And you can see, if we're going to look at this net reaction up here, we're going to have our classic benzene ring with nothing attached. And if you add in some catalytic AlCl3 and some alkyl chloride, in this case we're going to use ethyl chloride, then you can basically just cover up this piece, the piece attached to chlorine, and then that alkane piece you're going to stick onto the benzene ring. Okay, so let's see how it works. So let's take this ethyl chloride, and just like we did in the chlorine mechanism and the bromine mechanism, we're going to draw out our AlCl3. Since aluminum can accept a bond, chlorine is actually going to attack and bond to aluminum. Okay. I'm going to draw the result of that electron flow. Aluminum has a negative charge, chlorine has a positive charge. Okay, so just like in the chlorine mechanism, this bond is actually going to break, and chlorine is going to peace out with those electrons, right? Alright, so follow me on this. The result of this electron flow means we have AlCl4-, and we're going to form a carbocation, right? Right here, we're actually going to have a primary carbocation, whoops, that was ugly, on this ethyl piece, right? Okay, so something I'm going to highlight also at the end of the mechanism, but you see how we just formed this carbocation? There's the possibility in this mechanism for hydride and methyl shifts. So that's something that is going to always be a consideration when you do this mechanism. Okay, but let's just finish the mechanism out. So now that we've made our electrophile, right, we're good to go. We're good to bring in benzene. So if we draw our benzene, remember he's a hub of negative charge, and we have this positive piece right here. I'm going to use this bond right here to grab the positive carbocation. So remember, as we've said before, this disrupts the aromaticity of the ring. So this carbon is missing a bond, and you can see, right, I added 2 carbons off the ring, right? So that means off of this ring, I've added 2 carbons. Be sure to don't lose carbons, don't add extra carbons. Okay, so just like we had before, we need to recover our catalyst as well as restore the aromaticity to the benzene ring. So let's bring in AlCl4, right? Aluminum has that minus charge. And remember, this chlorine is going to leave with these electrons, and he's going to grab this proton, and the electrons in this carbon-hydrogen bond are going to restore the benzene's aromaticity. So let's do it. Grab the proton, electrons swing down, and I'm going to draw the products down here. We now have our alkylated benzene ring, right? Our benzene ring with more carbons attached. We have AlCl3. We've successfully recovered our catalyst, and we produced a little HCl. Okay, so just to talk about it again, and I highlight this on the mechanism worksheet, kind of summary guide that I've given you guys. Sorry. Whew. Every time you have this, we produce the electrophile in a Friedel-Crafts alkylation, you have to consider the possibility of a carbocation shift. Because real quick, if I kind of draw this in red over here, could you imagine if I had this complex with the aluminum catalyst, right? Let's say I had just this, so if I had isobutyl chloride, right, this guy right here, and then we attack the AlCl3, we have this complex. Well, when chlorine leaves, what does that give us but this carbocation? Except we know that it won't stick like that, right? Because this is primary, and he's next door to a tertiary carbocation with the hydrogen that can move, right? We're going to have a hydride shift. So if you were to use this chlorinated alkane, this alkyl chloride for a Friedel-Crafts alkylation, then you can bet your bottom dollar, or top dollar, or all of your dollars, that you'll have this carbocation to stick on the benzene ring. So something to consider. I've always, I made sure to highlight it on the mechanism summary I've given you guys, but how can we avoid this, right? How can we add carbon pieces without the possibility of a shift? Maybe you do want this carbocation. Well, luckily, there's another type of reaction called a Friedel-Crafts acylation, and that is our next and final mechanism. Okay, gang, Just give me a little more effort, just stick with me on this last mechanism, and then this video is as good as done. Okay, so just like in the last video, we're going to basically have a type of alkylation reaction, kind of, where we're going to stick a carbon piece on our benzene. Except this is Friedel acylation, right? So instead of just having a bland old alkane piece added to the benzene ring, we're going to have some type of alkane piece with a carbonyl straight off the benzene ring in the benzylic position. Benzylic position is whatever carbon you have straight off of a benzene ring. And this is good because how we saw those possibilities for either hydride shifts or methyl shifts in the Friedel alkylation, acylation, there's a 0% chance of a shift with a carbocation. And I'll prove it to you through the mechanism. Okay, so like we do all the time, let's take the piece we're adding to the benzene ring and kind of see how it's going to interact with our catalyst. Okay, so as you could have probably guessed, since aluminum only has 3 bonds, this chlorine on our piece that we're going to add to the benzene ring, on our electrophile, we're going to swoop in and attack that aluminum. If we draw the result of that electron flow, this chlorine now has a positive charge, while this aluminum is going to sport a negative charge since he accepted some electrons. Okay, so as you probably guessed it, this chlorine is going to leave, old hat at this point, and we'll have to draw the result of this electron flow. We have AlCl4 minus, and we're going to have this other piece right here, where we now have a carbocation on the carbonyl carbon. And here's the reason why there's no shifts, because if I draw some resonance for you guys in this red marker, we can draw some resonance, and that's why the carbocation is going to stay put. Can you see if I took one of these oxygen's electrons and swung them down, I could have this weird looking resonance structure, right? We never see oxygen with a triple bond, but this resonance, the fact that this carbonyl oxygen and carbonyl carbon are present, that prevents shifts from happening because we can draw this resonance and produce this ion called an Acylation ion. That's just for fun, you don't really need to know that. That helps the carbocation stay put. Okay, so really, we don't need to see this. We just need to see the form of our electrophile with the positive charge on the carbonyl carbon. So, let's now enter our benzene ring because the electrophile is ready to go. So if I were to draw the electrophile like this, right, remember this benzene ring is a hub of negative charge, so let's take this double bond, let's swoop in and attack that carbonyl carbon. And I don't need to push up any bonds, right, because we're not breaking the octet rule. This carbon right here needs or is capable of making a bond, so we're good to go. So remember, we disrupt the aromaticity of the ring, we didn't touch these bonds at all, and we're adding 2 carbons to the benzene ring, right? So straight off in the benzylic position, I have this carbocation and an additional carbon because that's 1, 2. And remember, this carbon down here in the benzene ring has a positive charge. He's now a carbocation because we use this double bond to grab our electrophile. Okay, so now let's reintroduce the oh, whoops, that should be an L right there. Alright, we should reintroduce this catalyst to help us restore the ring's aromaticity as well as reproduce our catalyst, right? So let's redraw AlCl4. That aluminum has that negative charge. We know that one of these chlorines is super cool, super fine, with helping us out by picking up this proton and then leaving as HCl, as well as having these electrons swing down, reform a double bond, restore the ring's aromaticity. So I'll draw my arrow over here, draw my products down here. We now have our acylated product, benzene ring, that is still aromatic because we restored the aromaticity. 2 carbon piece with the carbonyl in the benzylic position, straight off the benzene ring. We have our AlCl3, that's good. We've regenerated our catalyst, and a little bit of HCl to round things out. Okay guys, you will need to know these mechanisms. Any test that you'll take involving benzene and aromaticity, you'll have to draw at least one of them, I guarantee it. So do yourself and myself a favor, because I want to see you guys do well. Know these mechanisms. know them like the back of your hand. I guarantee someone is going to ask you to do this for points. And that's why I gave you guys that nice study guide, because I know my mechanisms are a little messy. You'll always have one place where you can look at it, have it see it done nice in text, as well as I have those bullet points highlighting various things about the reactions, like the shifts in the Friedel-Crafts alkylation. Okay guys, in the next video, we're going to get a little away from this the mechanistic aspect of EAS reactions. I want to show you some helper reactions, because eventually we're going to tend towards doing synthesis problems. So we need a few more tools in our toolbox. So buckle up.